Hello. So this was part of the talk I gave at the Peking University. So yeah, there was service maximization and fractionalization. So I feel like so I will not give the whole talk, but just give a small introduction about some of the works from the group, from myself and from my student and my postdoc. And hopefully, my group can attract some of the students and postdocs because the group of mine is rather small. So we have like 2 graduate students right now. So our group works on extensively on topological materials such as white semi-metal, Latinger semi-metal, crystalline semi-metal, topological insulators, the line semi-metal, axial insulator, magnetic wires, etc. So in addition, our group has worked rather extensively, starting from my graduate school time with my supervisor, Leon Balance, and others. So we worked on so-called spin-orbit coupled correlated material. This is really a large, vast, unexplored field of condensed matter or solid-state physics, where the system, these materials has a substantial spin-orbit coupling and at the same time, experience strong electron correlations, and many exotic and interesting quantum phases can emerge, and many of them have not been carefully studied, especially theoretically. There are lots of experiments, but the theoretical side you know, is not really that mature, not as mature as the experiments. So the group, has worked rather extensively in the field. So we will continue work on this direction. So recently, I had Konju Wu from Western Lake University. He used to be in UC San Diego, and we had a collaborative work on so-called model insulator with multiple components of local Hilbert space. And these kind of things appear in both quantum materials as well as in ultra-cold atoms. And Konju is a real expert in this quantum simulation of ultra-cold atoms. Work on the transition metal oxide interfaces, heterostructures. There has been a growing of efforts try to synthesize these materials, these transition metal oxides, layer by layer, with atomic precision, and as well as some clean characterization. So the experimental technique can be so-called molecular beam epitaxy, pulse laser deposition, and the hope is we'll be able to provide some degrees of controlness to investigate, perhaps to maybe engineer surface interfacial engineering of the many body collision phenomena from the strain, lattice effect, electric fields, external electric background voltage, crystal electric fields, and Young-Taylor effects, medical valence bonding by doping, etc. And we hope to to have some degrees of controlness of the many body phenomena, and eventually have some understanding. There's some experimental, most of our experimental right now. There's very limited theory, so some of my effort, our research is to work on this field. This is two works. This was a collaboration with Leon Balance a long time ago, and we recently revisited this field, studied the interfacial engineering of topological spin textures such as magnetic skyrmions. Work on non-form liquid metal. Both of works are not really published, unfortunately. So they are on archive and on review journal. So we generalize this topological band structure idea to magnetic excitations, propose these concepts with wire magnon, and propose this can be realized in some materials. and some experimental features of these topological manganons. We studied the how to detect the hidden orders. Hidden order are these orders that can they should exist, but we conventional like thermodynamic measurement, spectroscopic measurement cannot clearly identify these natures of these hidden order, these orders. So that's why this is called a hidden order. This hidden order, we clearly see this huge entropy loss in the thermodynamic measurement, but in some spectroscopic measurement, it's unclear. So there's some idea how to detect them with RICs, with neutrons, some selective measurement with neutrons. Yeah, some of these efforts in the group are devoted to hidden orders. So quantum spin liquids, we worked rather extensively in the field of quantum spin liquids, and we work on thermal Hall effects. Thermal Hall effect has been the active field of research right now, and many experiments and theoretical physicists are working on thermal Hall effect, the mechanism of thermal Hall effects. And we are writing a review paper on thermal Hall effects with my students. And we are interested in this quantum simulation in ultra cold atoms such as SO and symmetries of alkaline earth atoms, ultra cold polar molecule quantum simulation, synthetic gauge fields. Yeah, that's pretty much the sum of our recent interests. Yeah, so hopefully we can attract some students and postdoc to the group. Okay, thank you.